much for joining us, everyone, back at the Expo Innovation stage. We're so glad to have Jonathan Oliver here, founder, CEO, and CTO at Smarty. Absolutely, energy up. Also moderating in the chat, we have John Hickey, product marketing manager at Smarty as well. Thank you both for being here, and I'll leave it with you, John.
Awesome, thank you so much, Garrett, appreciate it. Okay, well, let's just dive in. Let's talk about cloud computing, and I can't tell you how fun it is just talking to a screen. It's just one of my favorite things to do all day. So we're just gonna talk a little bit about me just really quickly as we dive in. I'm a founder of a little software company called Smarty. I'm a technical founder in that I'm a software engineer by trade. That's kind of my passion. And Smarty, what do? We do street address verification. That's the simplest version of it. So when you type in your address, we're the one that pops up and says, do you mean this? At least if it does it right, that's what we do. And in addition to that, we have some address autocomplete, type ahead. Google also is pretty well known for that. They do it okay-ish. We have a lot more understanding of the domain. As well, we also do reverse geocoding, rooftop geocoding, and my specialty is helping bring to the tables the expertise that can do this at millions of lookups per second, billions of lookups per day, and finally trillions of lookups per year. So, all right, let's just dive right into the material. Why multi-cloud? And I'm going to cover this in pretty short order so we can get to the meat and potatoes. But one challenge you run into is that the network, everyone thinks, oh, the network's always going to be working. Everything's always going to be up. It's working all the time. Well, that's technically a fallacy of computing, or more specifically, the fallacy of distributed computing. This was a set of rules created at Sun Microsystems back in the day. There was originally 3 rules of distributed computing. It was like the network is reliable, bandwidth is infinite. And it was expanded over the years to like 7 rules, like, oh, the network is secure, and then ultimately I think it's like 11 or 12. They keep adding to it. In any case, the question to ask isn't if your cloud provider goes dark, it's when your cloud provider goes dark. And when that happens, what are you going to do about it? And this isn't just hearsay. This is actual documented cases. There are some great ones. I remember, oh gosh, this was July 2008 when Amazon was down for 3 days. It was S3. This is early in the days of cloud. S3, one of the base foundations of their system, was offline for 3 crazy days. Microsoft, somebody forgot to renew a TLS certificate. That's super fun. Google Cloud's gone dark, global outage, everything offline, so much fun. And then of course, multi-cloud, one thing that you can pay attention to and becomes more explicit is the idea of the egress tax. So most of these major cloud providers charge 10 cents a gig for their cloud egress. And that's quite expensive. Especially considering you can get, with pre-cloud, buying bandwidth from Cogent or L3 was significantly less expensive than that. Now you might argue, okay, then the cloud providers' networks are superior, and in many regards they are, but at 10 cents a gig, it is a huge tax. So by having at least an understanding of the egress tax, you can actually design your systems in a way that works through and around that, rather than having to be surprised by it in the end. And then finally, when you're only on a single cloud, well, you've got all your eggs in one basket. So it's just you're just kind of asking for it. And there's been large accounts on any of these providers where they will be, I'm going to use the term randomly disabled, where all of a sudden they're completely offline, and there may be some internal reasons why that we don't have any awareness or insight into. But what you don't want is to all of a sudden wake up one morning and at 3 a.m. more specifically, not the typical 6, 7, 8 a.m. time where it's like, oh, I wonder what's going on. It's the 2 in the morning, the system's burning down. Really, all of this comes down to that. This is a sleep thing. We all want to be able to sleep well through the night, and we don't want to have our accounts randomly disabled. And also, when you make a config change, who here has made a config change that, oopsie, it took something offline? I think all of us have done that. And the good news in most cases that we realize it pretty quickly. The challenge that you run into, though, is if you're only in a single cloud, your deployment strategies have to be a little bit more cautious, because if you make a config change and roll it out, all of a sudden now it could affect everything in that facility. And if you only have one facility, the entire thing's offline. So multiple facilities actually enables or makes it harder to do a config change. And this is a good thing that could have lots of negative consequences. Okay, so let's just talk real quick about IBM and Honeywell. So this is back in the 1960s. you were writing software, you would be writing software that was processor specific. So you would write it to the given instruction set of the CPU that you were operating on. And if you wanted to, recompiling did exist in some very primitive forms, but not in the concepts or understanding that we have today. If you wanted to have your software running on newer hardware and so forth, well, you had to rewrite your software. Well, that got old pretty quick because software is very, very new in the modern sense. And already at this point, software is becoming very heavy. It's taking a long time to write and to debug and so forth. And so Honeywell, the thermostat company, yes, that Honeywell, the thermostat company, they developed a microprocessor called the Honeywell 200, which allowed you to run natively the IBM 1401 instruction set. So it was emulating it. So this is a really cool thing that they did, that you didn't have to rewrite your software, and yet they had this compatibility layer. And so you were able to get 2 to 3x the performance out of your software just by upgrading the hardware, which was then at that point cheaper to do. So now IBM System 360, this is a system designed by, Gene Omdahl. He's the guy that coined Omdahl's law. And that actually has a lot of really cool applications in like organizational efficiency and the number of people that you have in an organization and like how fast you can do a particular job and so forth. Anyway, Gene Omdahl, he developed the IBM System 360, and it had a whopping 34,500 instructions per second. Mind blown. And 64K, not of RAM, but 64K of memory. That was a beast. In any case, IBM System 360 also recognized this problem, and they later incorporated the IBM 1401 compatibility layer into their system. Okay, so then let's fast forward a few more years. So that was about 1965 or so. So let's fast forward to Bell Labs. This is about 1972. Dennis Ritchie's working there, and he's got this problem. He's working on a PDP-7 mini computer, 500 kilograms, 1,100 pounds-ish, 1,100 pound mini computer. And there's a picture of it right there, the PDP-7. So he's writing this new OS for PDP-7. And let me back up. He's not only writing a new operating system, he's writing a new language to write the new operating system. And of course, this is all history. So, and one thing he recognized was he wanted to create this idea of the compiler, because he wanted to abstract the processor instruction set from the processor itself, and from the software rather. And so he worked through this whole thing. So the idea behind this was he wanted to have same code and multiple processors. Now, C is crazy because C is an awesome high-level language. Now, when I say that, I always get strange looks like C is a high-level language. Yes, C is an awesome, amazing high-level language. And so Dennis Ritchie created the C language and the compiler and so forth. And there were multiple individuals involved in that project. And then he also built Unix. Now, look at everything that's running now on any computer practically in the modern world, and it's written in C, or it's written on something that was written in C. So if you're writing in Java, you're writing in Go, you're writing in Visuals, in C#, et cetera, you're running on C or C++ in some cases. And the base of that underneath is almost always a Unix or Unix derivative. The modern world is built on C and Unix. Okay, so now you're writing software. And now we're going to use a language called, we're going to use C or something similar. So we've solved this CPU microprocessor instruction set problem, but we have a different problem. We've got writing application state. So back in the day, again, this is very, very common. You were writing an accounting package. You worked at General Motors, you worked at General Electric, and you were writing some accounting software to track the number of vehicles sold, whatever. And if you wanted to persist application state, you would need to embed the code that understood the physical layout of your storage, tape, disk, whatever, into the software itself. It was a really big deal and a really big problem. So if you changed your storage subsystem, you had to change your application code. So that, again, specific sectors of the disk would be embedded in the application code itself. So it's you may often have to rewrite large portions of your code as a result. So now, how do we solve this problem? This is where inversion of control comes in. There's this concept known as the virtual call table, and it's something that's worth Googling, but basically it's a software instruction that allows you to jump over to an implementation. What that means is if you were to talk about the disk subsystem, you would jump to the implementation that allowed you to write to disk the specific type of disk that you were dealing with. And this is all, so this inverted the dependency flow, where rather than taking a concrete dependency on a tape drive, or I don't know if any of you guys remember like using audio cassettes. Audio cassettes was something that that was often used for storage. You would often use audio cassettes to like write to, again, you'd stream it out and so forth. So the way that you would write things was very different depending on the implementation. So, and you could plug different ones in now using this inverted dependency flow. So application code now at this point only needed a pointer to the particular subsystem, whether it was storage or network or whatever, and the particulars of that storage could be dealt with in the implementation details. So now we could all of a sudden plug in different implementations for storage and so forth into the software. So that's just simply the concept of an interface. So today, modern software, what does that actually look like? Well, without being rewritten, most software can run on various instruction sets: x86, ARM64, PowerPC. Anyone remember MIPS? Spark processors, those are the days. Those are amazing times. And then you could also write the same software, and without making changes in code, you could then run it. Now you can run it on Linux, Mac, Windows, Unix, the BSD derivatives, Solaris, and Solaris derivatives, including Illumos. And this is all powered through these the runtimes. The Java, the language, not really. It's the JVM that's really the interesting bits. And the JVM, of course, has been expanded over the past decades to allow for different languages. The CLR, C#, Go, of course, Node. These all different have. Ruby, of course, has the Ruby has an official runtime. All of these things are just amazing. So the runtime environments under the languages insulate our application from the code, our application code from the quirks in the hardware, the operating system, the CPU architecture, et cetera. In fact, I think it was like Unix, it was like system, oh gosh, there's like, there's like system 7 and system 3, I don't remember the particulars, but there's like different iterations of Unix. I think system 3 or iteration 3, I'm trying to remember the particulars. That's where they figured out the storage subsystem problems. Okay, so because of the runtime environments, we really don't have any of these problems. Now, of course, the promise of Java was write once, run anywhere, but the delivery of it was write once, debug everywhere. Even so, most of that has been figured out by and large, and none of these problems really plague us today in any meaningful way. So this is the era of modern computing with appropriate level of abstraction. So this is a huge trip. I just spent a ton of time on memory lane. Why? We have implementation-specific behavior akin to CPU-level instructions and akin to storage-level instructions strewn throughout our software. And the moment we see it that way, all of a sudden it becomes understandable what we can do. So we have our database storage layer that's sprinkled. We have SQL statements all throughout, and SQL-specific statements all throughout our code. We have our transport layer, which is often hard-coded to HTTP. And oftentimes we are making cloud-specific API calls to AWS and so forth, Google Cloud or whatever. And it's not that, at some point our software does need to make an AWS call to SNS or SQS or whatever the service might be, or Google Cloud to their storage, or Microsoft Azure, whatever the case may be. But we need to have our code insulated from that. So let's go through that. And one of the reasons we actually do this implementation specific behavior, where we just code it in with HTTP, just code it in with an Oracle database, AWS. The reason we do all of this is it's easy, and it's an unneeded abstractions. We got all this extra complexity in our code. And of course, this is kind of a joke. Oh, we better build in support for Sybase just in case, or you never know, we're going to switch from HTTP to Gopher as a transport mechanism. And oftentimes it's really someone else's decision on which cloud provider we use. So, and no one ever got fired, of course, for using IBM or Oracle or Microsoft or AWS, et cetera. So what we want to do in our software is we want to present people with a choice. So we may not have the decision authority on which technology we use, but we can structure our software to allow for alternative implementations. And this is now the software interfaces, AKA the virtual call table. So please forgive this. I have 10 lines of code to present this in to make the slide legible when I was giving this presentation in person last week at the conference. But yeah, 10 lines of code. This is terrible, terrible code in every possible way. It's C#-esque. There's so many different things I would not do here in real life. Well, granted, this is also a bad example, but right here we're looking at S3. We're newing up an S3 implementation right there in the upload profile photo. and we are dealing with HTTP as a transport protocol, and we're uploading to S3. Again, we have no error handling. This is beyond the scope of what we're trying to do, but ultimately uploading a profile photo, okay, great, to S3. All right. Now, a less bad, let me go through the choices. So what if we wanted to change from S3 to Google Cloud Storage, Azure Blob Service, or maybe not a key value cloud thing, but something else is key value, SQL, file system, whatever. You know, what would change in our code? Let me go back just for a second. So right here, it's AWS specific. We can't do anything about it. Okay, so we need an interface. Okay, all right. So this is a less bad example. It's not a great example, but there's a little bit more to look at here. So we have an interface, cloud storage, and notice it also gets passed in the upload profile photo. And you can do that in a number of different ways. This doesn't have to be passed in. That's your dependency injection of choice. Please don't use, oh gosh, Spring and some of those other ones. There's newer ones that are nicer. But this right here, it doesn't even deal with HTTP. It's actually just doing like, okay, here's my source stream, and here's where I'm uploading it to, and then upload the thing, and then did it work, yes or no? And of course, it's big fat to do. Please do some real error handling. So principle is when you need dynamic variability at runtime, you've got to have an abstraction. And this is oftentimes, again, it's a database, it's storage. Think when you're making an external call outside of your software, you've got to have an abstraction. And again, this is a lot of the low-level stuff has been provided for us by the runtime, but cloud doesn't exist. It's so new, we don't have these abstractions. HTTP is finally, Java, it's like finally kind of officially supported. Was it Java 11, I think. Java came out in 94, and it's like, HTTP, what's that? It's like HTTP was like the realm of Netscape and their expensive server software at the time. In any case, cloud is in the same realm. It's so new, we're starting to get some abstractions, but it's not great. So we're trying to insulate our business logic from the environmental details, just akin to the embedded. This is like embedding sector-based storage logic in the app code. Okay, so if you have any external dependencies, you can say, okay, load user profile, as opposed to select star from profiles where. You do not want to be doing implementation-specific code like that. And this is all outlined more, and it's a concept by a guy named Alistair Coburn. He was one of the Agile Manifesto guys. He calls it hexagonal architecture, otherwise known as ports and adapters. There's variations on this. It's pretty awesome stuff. Okay, so what we're trying to do then is protect and insulate. This is kind of a recap, but then we're going to dive into some other stuff. Protect and insulate our business logic as much as possible from the external harsh realities and craziness of the real world. So that's, and interfaces allow us to do that. So, and also, this is another cool thing about interfaces, that we can all of a sudden start making technology decisions. They become an implementation detail. What I mean by that is, so if you want to use Redis, Memcache, Hazelcast, name one of the other hundreds, tens of dozens, I should say, of caching technologies out there. Well, all of a sudden you can just pick one as long as you've got some implementation code that wraps up in a nice compatible way, Redis versus Memcache. And of course, and then you can start looking at other attributes of Redis and Memcache. We'll get to those in a second. If your database, okay, well, do you want to use MySQL, Postgres, SQL Server, SQLite? I mean, there's all, I didn't put Oracle on here for a reason. Sybase, no, thank you. And of course, messaging, if you want to use Rabbit or Kafka, Pulsar, SQS, as well as any of the other Google Cloud or Microsoft technologies for that. Great, have at it. And then I had way too much fun with this one. Like, here's our transport. Now, transport layer protocols change all the time. It's like, HTTP has been the thing. It's, oh, we got to use that. And I put Gopher in there because I love Gopher. And then MQTT is a thing. There's Stomp, there's SMTP. AMQP, of course, is a RabbitMQ thing. gRPC, there's WebSockets was a thing for a while. And then it's like, okay, and I don't know if any of you guys remember COM Plus, or even DCOM. And I think Java had one. No, I'm trying to remember who it was. Corba, I think it was what it was called. These are all, like, again, transport layer protocols. These things seem to change pretty often. Maybe we should think perhaps about insulating our code from the particulars of HTTP. If you're using HTTP in the depths and the bowels of your code, then there's a bigger problem. And so what you're trying to do is you're trying to keep HTTP at the periphery, and this goes back to the hexagonal architecture idea. Okay, so the decisions about which software package to use and technology stack even are no longer accidental. It's like, oops, I guess we're doing HTTP now without giving anyone a choice. And you can start to make tech trade-offs based on licensing requirements. It's like, well, what Right now we can largely decide what operating system to use and even CPU microarchitecture because of the JVM, because of the CLR and so forth. And the CLR only recently, yay Microsoft, they've done some amazing work on the CLR. It's crazy awesome now. But even Ruby and Python, all these other ones, all the work that's been done allows you to vary your tech stack based on licensing. Do you want to use Windows? Do you want to use BSD? Do you want to use, take your pick, Linux, and which flavor of Linux? Oh, I got to use Red Hat. I got to use, anyway. But also, okay, well, how familiar is the team with a particular technology? Okay, do we know how to use this thing? Does it allow for clustering? Does it have durable storage? And also there's the CAP theorem components here. So now there's a few other quick things worth mentioning here. So this is generally speaking how to get your application insulated, but beyond the application, there's other little things to consider as well. So let's talk about ops and ops engineering. So the operating environment and the deployment stack. So if your whole mechanism to deploy software is all about baking AMIs, you're going to have a hard time migrating to other clouds, generally speaking. I know that Netflix had a whole build process and build pipeline where they would always bake new Amazon machine images. And it makes it more tricky to migrate to other clouds. So containers, Docker containers, I don't even know if we're allowed to use OCI containers, whatever we call them now. Containers make it a lot easier to move between cloud. Now, I'm not saying that you have to use containers. It just happens to be easier that way. My preference is I try not to use containers if I can help it. But coming back to, again, multi-cloud, well, if you're using AMS or AWS AMIs, it's going to be trickier to move versus Elastic Container Service versus Kubernetes. Okay, and Kubernetes, all you have to do is some hosting specific YAMLs, some cloud provider specific YAMLs, and you've got a pretty compatible system. And generally speaking, you try to insulate all the layers. So the more dependencies you take on a given cloud or ecosystem, the harder it's going to be to migrate. So think of it like this: the closer you are to the sun, the more likely you are, the stronger the gravity that keeps you there. There's some advantages to being close to the sun, planet Earth, warmth, and so forth. But at the same time, if you're trying to escape it, trying to get into, the cost is going to be much, much higher, like getting out of orbit into space. Okay, so which control plane are you using to make that happen? And ideally, your application code shouldn't care. We've talked about, again, Amazon versus any other one, but your control plane. So Kubernetes is kind of the one that's dominating the space. And it's supported using Google Cloud GKE, which has the best support. Microsoft Azure has their AKS. There's some quirks with it, but it works pretty well, especially in the middle. If you get around the edges, sometimes there's some rough edges there. And AWS has their EKS, which I think I can't speak to this, but I think they kind of begrudgingly offered. And it had some issues for a while, but there's been some significant improvements since its debut. And I think largely it's works pretty well. But then again, they're not the only games in town. DigitalOcean is rocking it. They've got some amazing stuff. We use DigitalOcean. We use Google Cloud, Azure, AWS, DigitalOcean, Linode, and I'm putting this up here. We use Vultr as well, and they're just awesome. But in addition to Kubernetes, there's other stuff out there that's really worth taking a look at. The HashiCorp guys, the guys that do Vault and Consul and Terraform, we'll get to that in a second. They have a thing called Nomad, and it is amazing, especially if you're doing on-prem or multi-cloud. You can install Nomad, and it'll be your control plane for all of your apps, and it works with Java apps and just Go apps and C# apps and container-based apps, and it is amazing. But in addition, and lastly, I should say, the tooling that you use to talk to a provider, infrastructure as code. If you're using CloudFormation, again, this is the gravity problem. You're kind of tying yourself specifically to AWS. This is where Terraform, the HashiCorp stuff, really shines. It allows you to break free of AWS specific and other provider specific stuff. So if you're going to provision resources, try to use Terraform or even Pulumi. That's another one. So this is kind of the wrap up slide here. Interfaces are amazing. They also help with unit tests, again, mocking storage and database and so forth, or plugging in different implementations. Again, you want to try to use containers as much as you can. If necessary, your control plane, try to use Kubernetes or similar, Terraform for creating the infrastructure and whatnot. Here's the last word of advice: start small, do something small, try it out, see how it goes. And the one topic I did not get to cover is the massive, massive problem, which is a 10-hour talk on shared mutable state between clouds. There just isn't time to cover that. So thank you very much.